So hello, I am back. I have some misunderstanding about the hours. Are you there?
Yes, we are.
Yeah, thank you.
Yes, we are.
I just want to know because of this mistake. Thank you. We can go further. So now we can go to the examples of Earth observation. So that's unique source of information. And why unique? Because you can gather information about big area, about whole country, of region, of continent. So and the use small number of images according to some photogrammetry or whatever other air photographs. So Earth observation can provide insight into phenomena that are...
Your screen is black.
Sorry, I didn't share with you. I hope now it isn't.
Now it's good.
Now it's color. So, like I said before, on this way, you can collect some information or show other people information about certain surface. So this map is produced using the Joint Research Center Human Settlement Layer. A global high resolution, it's a multi-temporal dataset which measured the extent of build-up areas. So on satellite image, someone extracts the build-up areas. And according to that information, not information from the ground, how many people live in some regions or whatever, no, according to the build-up areas, the settlements, the cities and villages, and the surface of that villages and towns according to the vegetation surface. So this map are produced on this way. After classification, they collect for each this region in right color, and you can see the built-up area. It's the increasing of this area. Like I said before, from 1990 to 2014, the experts took the pictures from the archives, do the classification in the beginning in 1990, and maybe every 5 years or 10, and the last one on 2014. And according to that movement or spreading of the settlements, they produce this thematic map. And you can see the differences between 19 and 14, 1919 and 214, and this is the percentage of differences on the certain ground. So you can see where is the greater increasing about built-up areas. So we can presume that's around the main cities or larger cities or whatever. So this is one of purpose to use that Earth observation and remote sensing results. The other one, it's the calculation of spectral indices. This is the vegetation index. So that shows the status of vegetation on our planet. So the blue areas which have the most green vegetation, it's the vegetation with the better status. So are most often forests or dense woodland. Southeast Asia, Central Africa, you can see that truly they can also be very productive grassland, as in, for example, Ireland. Yeah, you can see the Ireland is all in blue. The yellow and white regions are largely deserts or arid savanna which support little or no vegetation. So when do the mosaic of all satellite image of Earth, or do with every image and do the mosaic of these images, someone can see the status or the density of vegetation on our planet. So if we look to Africa, I put here some little video. You can see the changes from the 1981 to July to 2000. So you can see the change in the seasonal change and in changing in the timeline. So this call in the remote sensing change detection. So detected, its left one is the one still image from 1 year, and the right one, it's like I said, the image which showed the differences between the vegetation status in this almost 20 years. So the other use of remote sensing results or Earth observation data is world fire map. So every wildfire or fire whatever in a planet they exist or they took place can be put in some layer in the GIS and also in some timeline or for prediction. Maybe this is part of the planet where experts predict where this wildfire can take place. So user can provide and download imagery in different band combination and add overlays on the imagery of active fire detection or with the fire which are done, which are finished. So that is also capability of Earth observation and remote sensing data. According to thermal images, or like I said before, someone can produce the burn ratio. So the calculation of the various bands of images to get the surface which on which was a fire. So this information is very usable for GIS or for deforested surface, because when the fire, like I said, destroyed the wood, so someone can after that go to put another one in the soil and wait another 10-20 years to get the tree. So it's the other opportunity that can be done with satellite images. It's a radar one. It's a flood map. Someone can produce the flood maps. It's an example from the Serbia and Bosnia and Herzegovina. It's flood delineation map over the village of Balaton. So left, you can see the radar image. On the radar image, the water surface are black. So you can see the river and the water around that river. And on the right side of slide, you can see the thematic map of this occasion. So from radar images can extract the surface of flood, and that can be shown over some georeference image, like satellite image or some orthophoto map in this case. So that's also can be done with remote sensing methods. So lava tracking and mapping on the Spain this year. You can see on the left side I don't know what this is, status of 20 September. You can see that the red area on the right hand side. This is the 20th of September, when the lava can go out from the volcano, and on the right side you can see the whole map through some days when the experts monitoring these events. So the capability of remote sensing, it's monitoring some specific phenomenal object. Here is object, it's lava, and the movement of that lava through the time. And this is the one example of urbanization. Like, see the first one, the first example. You can see the map of large ring of urban areas. So here you can see how can you monitor and get the different surface from the different times from the same places. So this is this one city in China. It's 1988, and you can see, look how they look 8 years later. So with the naked eye, you can see the large difference. You can see here in the left side of the image, it's upper left side, it's a new airport is built. And here we can say the Chinese thief and get the soil from the sea. You can see the large surface. They get a large surface of soil according to in this 8 years. So this is also called, like I said, the change detection, and you can monitoring the spread of some urban areas through the time. This is just images, but if you do if someone produce the classification, and then that one can see, or I'm speechless now, that they can yes, see how much the time or build-up area is grown, or how much some vegetation are lost in this urbanization. So now I want to share with you a brief history of remote sensing. I think it's good to know some specific point in the history of remote sensing, because it's not a very large history. So it's remote sensing is most commonly associated with application in geoscience, ranging from the earliest aerial photographic surveillance to space-based Earth observation. So its remote sensing is developed by purpose of observation of the Earth, like we said before, and they sensors create images by means of reflected or emitted electromagnetic energy. So we can say the first de facto remote sensing specialists, like I said before, were actually astronomers who studies targets remote from the Earth. That kind of studies astronomers do today also, but today we, or remote sensing guy, or every guy which wants information about the Earth, it's more interesting in the Earth. So the human put the satellites in the orbits and get information, Earth observation, from them. Some of the two major milestones in remote sensing history are the investigation and development of photography and aerial platforms, because for remote sensing we need imagery, photograph image, and to produce image you need the sensors, and when you have the sensors, you or someone want to put them on some platform to get a bigger picture. So it's logical in history of remote sensing. It's two major things are photography or sensors and aviation. So that starts from the Wright brothers and his, I can say some aircraft, and camera obscura, which we have first information from 11th century from the Arabical world, and in the 16th century it's for a real definition of this camera by Leonardo da Vinci, and after that aviation go through this stage, airplane, helicopters, and now drones, and finish with the sensors on the satellite, which are in orbits around the Earth. So it's one of the first camera. It's like a flat, like a small flat, going through this. It's analog camera, and going today to digital camera. It's an aerial digital camera with blue, green, and red wavelength light. That range of electromagnetic spectrum created the images on this camera, and this black it's for photogrammetric image. So it's this briefly in the beginning of the 19th century. It's discovered the infrared, and the first recordable photography. It's also 35 years later. It's in 19th century. 19th century is also its beginning of practical photogrammetry, And the theory of electromagnetic energy, it's also important for remote sensing. It's also in 19th century, and in 20th century, people get the photographs from the planes, airplanes. So in this time, it's from 30th to 40th year of 20th century, it's the development of radar in Germany, because the Europe and world, it's prepared to the war, and aviation came better and better, and radar is some purpose to prevent some larger damage from the aviation. So it's normal they took the place in this year, because sadly it's almost everything which connecting with remote sensing or photography and aviation, it's have a great stick with military use. So in 60 and 70s years of 20th century, first use of thermal remote sensing. This date is, and this year, it's very special for human beings. It's 1972. It's the first civilian satellite are launched, and in 19th start developments of the hyperspectral, and in 80s and in 90s start with LiDAR and such kind of sensors. So also it's first photography of the Boston and history. Like I said, it's most investigation about photography and platforms are linked with the war, so I don't read all this, but just one, maybe you can say it, silly thing. In 1903, the Bavarian army has used the pigeon. Like I see, you can see, it's no joke. They used the pigeon for the spying of enemy territory and get they get the picture like that. So does they picture get some use information? I don't know, but it's one story from the history. You can see the small some small sensors in that year also. And now it's civilian application. It's better to talk about them, but after the wartime training and experience of large number of pilots, cameraman, operators, and photo interpreters create a large pool of experience. So they gathered a large experience of that's things of shooting, interpretation, whatever they need for collecting the information from some area, and they start to work in civilian firms. So by the late 1950 era, photography had been institutionalized. So everyone who can bought some camera or a sensor can took the picture. So like say the first meteorological satellite launched in 1960s or also 20th century, and like I said, the 1972 launch of the first Landsat, and from that time now we go to the WorldView 4 or something like that. Its first satellite have the resolution of 80 by 80 meters, and today's modern satellite have about 30 centimeters revolution, spectral revolution. resolution, sorry. So that is for that. Now I will, with second presentation, follow. I need to share that with you. So, now I think I am. So now we will talk about some, I said real remote sensing. It's the electromagnetic spectrum, and that is the thing which we use for creation of images. So you don't see that, but because of that existence, you see the things around yourself. So we know the nuclear reaction on the sun produced that electromagnetic spectrum, or we can say radiation, and that radiation transmits to the space without experiencing major changes. So before reaching the Earth's surface, that spectrum, so this radiation passes through the atmosphere, like I said before, and some part of it is reflected upward from the Earth's surface. So the major part of this energy reflect, and some part of this energy Earth absorb. So in this radiation that forms the basis for digital imagery of Earth's surface. Like I said, it's the nucleus for the production of the digital images or every kind of images. An artificial source can also produce energy that is reflected from the objects and reach sensor. Like I said, if you want to take a picture in dark, wherever you be outside or inside, what you need the flash on camera. So when to use the flash, when you or some of you or someone take the photograph inside or in some laboratory, then they use artificial illumination, artificial energy, irradiation to get the picture about surrounding objects. It's the same things. The flash create the energy go towards to objects reflects the energy, and the sensor took the reflection on yourself and produced the image. So what irradiation? So irradiation and solar radiation. Irradiation is the energy or radiation from any source. The amount of incoming energy emitted by any source and any wavelength, which falls on unit of the surface. Sorry, it's amount of energy on the per units of surface. So when referring to the radiation of the sun, when we talk about sun irradiation, that we call the solar radiation or insolation. So it consists mainly on energy emit in the form of short-wave radiation and light. We saw part of this electromagnetic spectrum light. Like I said, we don't actually see the light. Now, if you look to the window, you don't see the light, but you see the objects because they light exists. Because that light, that's energy, that's photons, it's the nucleus of the light. The hit to the objects, reflect from objects to our eyes, and that's how we see the picture the objects or phenomena around us. So what's this? We said that the electromagnetic spectrum are energy or have some energy. If you see that blue line, that's line show us the amount of solar energy in the vacuum outside of atmosphere. So in the space where the photons doesn't have any obstacles, so they go through the space, and you can see the major amount of energy is the visible part. Visible part here is from 400 to 700 nanometers. Like I said, in this part of region, our eyes can recognize. So only this part of spectrum we can use for seeing the objects around us. Now, I don't know if they know it's a cat or dogs. I also think they use the wavelength in the infrared. That's from 700 to 100 nanometers. That is the portion of spectrum. Because of that, they can see better in the dark than humans are. So this blue line, like I said, show the amount of energy. This surface below that line, it's amount of energy of insolation outside of the atmosphere. This yellow line show us, so the surface behind its yellow line show us the amounts of energy of electromagnetic spectrum in atmosphere. So you can see that differences from the yellow, in the surface from the yellow to blue. That's all part of energy, irradiation, the atmosphere absorb. So that kind of photons or energy doesn't reach the Earth's surface at all, or reach in small amounts. So the reason of that, because in atmosphere are the small particles of water or carbon dioxide, of dust. So all that kind of particles absorb photons, and they don't further going to the atmosphere, to the surface. So the atmosphere is the reason that we alive, that we exist on Earth, because I think you know, but they absorb mostly of its ultraviolet part of part of electromagnetic spectrum is before blue one. It's here, you can see it's a large amount of energy that the atmosphere absorbs. So preserve the life on Earth. So that's the problem about global heating, because much particle go to the atmosphere from the human, you know, the amount of that particle are increase, and the photon cannot lose the energy, because photon have kinetic energy, and when this particle of dust or water or whatever exist in atmosphere, they absorb them, that kinetical energy transform to the heat energy. So on that way, the atmosphere going warmer. So here is the visible part of the spectrum. It's from 400 to 50, and it's the blue one, the green and red part of spectrum, and this from the 700 to 900 or 100 is near infrared. That's the main channels which most people use in remote sensing. Other are thermal and microwaves. So if I show you just that part of spectrum that range from 400 to 900 nanometers on x-axis is wavelengths, and in the y-axis it's insolation, it's energy. And we can see from, like I said, from 400 to 500 it's blue one, it's the green, red, and after that it's the near infrared. So you can see that the large parts of energy are in a green portion of spectrum, range of spectrum, and when you see or looking at the photograph or images, and images in green or green band of the satellite images or whatever images can be, it's and are most brightness image of that tree one, blue, green, and red. So that is the amount of isolation in range of spectra from 400 to 900 meters. It's from visible to invisible and near infrared part of spectrum. So you can see the average amount of that irradiation in the world from I don't see the year, sorry, it's 2013. You can see it's average amount of irradiation on the whole Earth in 2013. So it's logical, it's closer than Ecuador. It's this irradiation is bigger, and closer the poles, this irradiation is smaller. Also for Africa, the scale it's from the 2004 to 2010. It's average annual sum, yes. Average annual sum of horizontal irradiation in Africa and so for that purpose also can be used the informations of Earth exploring. So this kind of information are collected the sensors which don't produce the images, but they just measure this radiation which came from the surface, which reflected or emitted from the surface to the sensors on the satellites. And now you will see and heard, it's better, it's to see the better explained to a little film of 5 minutes. It's what is it electromagnetic spectrum. I think they better explain than me, and we will see, or we will heard after 5 minutes.
Doctor, we can't actually hear anything.
No,
Yeah,
sorry.
there is no sound.
Yeah, there's no sound.
Sorry.
Oh, thank you for fixing it.
No. It's because of this one. So
I think if you open it directly on YouTube, it will be able to play some.
yeah. It's a better thing. So just me a minute or two to find this. Hmm. Sorry, it's a better way. It's also 2 and 45. It's 50 minutes to 3. So we a break here, and when I prepare, we start in 3 o'clock.
Okay.
That's best. Sorry,
You can-
someone can.
You can share the link with us.
Yeah, when we start, I show you. I will prepare for this. You will see that.
Okay.
Okay, thank you.
Thank you. That would be better.
No problem. Hello, here we go again. Now, I think you will see what you need to see. So let me show that. Do you see now?
Yes.
Yes.
Super. Great. Then listen and we will.
I don't think
Back.
there is sound.
Yes?
There is no sound.
No sound.
Yeah.
No?
No.
No. Andrija,
Da.
kad počneš šerati, imaš opciju uključi zvuk.
Gdje?
Kad počneš šerati ekran.
Dobro. Jel to u onom padajućem izborniku ili? Nemam to nigdje.
You can put the YouTube link in the chat box, please.
Excuse me. Hello?
Yes.
Just a minute.
Andrija, u onome padajućem, ne u padajućem, u ovome share ekran imaš ovaj gumb include computer sound.
Gdje?
Kad ideš šerati ekran,
Da.
ovo gdje je kućica, skroz gore desno imaš include computer sound.
Nemam.
Excuse me. Hello?
Yes.
We can change the setting of the Microsoft Teams from setting, device setting in Microsoft Teams, and we select the audio from the device, from the computer.
Sorry, once again.
There is a drop list of three dots, and we choose the device settings in Microsoft Teams, in the main menu of Microsoft Teams. You have, I have on my screen, I have the some icon beside the raise your hand icon. It is three dots. From
Yes,
this
yeah, I see, yeah.
device.
Uh-huh.
Yes, device settings.
Yes.
And from this we can select the speaker or the source of sound from a list. So you can choose the speaker from the devices. Not you will have some options according to your device.
I don't have that option. Sorry, but I put the link in the chat.
Okay. Anyway, I watched this this video during the break. It's very nice.
Yeah.
Thank you.
Thank you.
Nothing. Thank you. No, I don't have that.
Andrija, and please, you have 5 raise a hand if you, ako možeš proći pa pogledati. Valadia is first. Raise. Valadia, Yasmin.
Ne vidim to. Aha. Sorry, just you have a link, and now it please look at that video for 5 minutes, and I'll be back after 5 minutes.
All right.
Okay.
Okay.
Are measured in millionths of a meter, nanometers. The number of these crowns is fantastic.
So you can see this now. We're going to further. Sorry for this inconvenience, but I think you see something, and now we will talk about that. It's the same thing I will tell you now, but this video, it's more comprehensive. So electromagnetic energy travels in waves and spans and broad spectrum from very long radio waves to the very short gamma rays. So you can see without waves, our life, I don't say will be miserable, but much electrical devices doesn't work properly or without cord wire. So the human eye can detect just small part of this electromagnetic spectrum, like we said before, like we saw before. It's we call that the blue, green, and red part of the spectrum. This is the main color, and with that color, you can, when you mix them, you can get every other possible color from them. Some the electromagnetic waves that's we said travels in waves, but what travel? Who travel on waves? That's the photons. The photons is the smallest parcel of the electromagnetic waves, and that photon surfs on the waves. So they don't travel through the space on the right manner, but in the sinusoidal. So like you see in a video, the electromagnetic spectrum, it's consists of two main fields. It's one electric and one magnetic, and in the same time, the particles, the photons, have the maximum and minimum amplitude from these waves. So like you see the right way, the photons are something with surfs on waves, and like this, they go through the air with the different frequencies, and all these frequencies and all these photons, which we don't see, they create some incoherent light. So that's the light or electromagnetic spectrum. It's sustain of a large number of photons, just simply like that. So in video you can see the dimension of some waves, like some bacteria or needle point or protozoans, your molecules, atoms. That's the some picture which want to show the largest or smallest waves, which all produce. That's that's all the have the energy which go through the space. On the right hand side, you can see the particles of the wavelength, or that's the numbers of the wavelengths of some part of spectrum. Like we said before, it's a visible part of spectrum is from 0.4 to 0.7 micrometers, or 400 to 700 meters. And near infrared, it's up to 1 micrometers. It's from 0.7 to 1 micrometers, and that's the most usable part of the spectrum. So on this slide also are shown the some biggest part of the spectrum. It's ultraviolet. It's before the green one, before the visible. Visible, I don't want to say anymore. Infrared, it's the very large part of the spectrum, but just near infrared, it's from 0.7 to 0.1. It's used for with visible one, and the border of reflection and emission is 3 micrometer. So every wavelength or every photons which surfs on wavelength 2 3 micrometers, they use for reflection. They create the image like we see on digital image, or which the digital image in color, what we see in every day. And after 3 micrometers, all that energy used to create the thermal images or radar images, and we talk about emission. So the border of between reflection and emission, or using the part of spectrum for reflection or emission to create the images, is 3 micrometers. So every object reflects radiation that has been emitted by some source. So in remote sensing, we trust that every object reflects on different manner, on different ways. So that's the main thing to use for the extraction some objects from the images, because different objects need to have a different pixel value. So with expression of objects of absolute zero, all objects emitted electromagnetic radiation. So the first one is reflect, everyone reflect radiation, and the second one for emitted energy, every object emits electromagnetic radiation. So by recording reflected or emitted radiation and applying knowledge of its behavior as it passes through the Earth's atmosphere and interacts with objects, remote sensing analysis develop knowledge of the character of features of the scenes. In other words, like I said before, vegetation, water, soil, and built-up objects are the main objects. And after all automatic or every other analyzation of the digital image, someone needs to analyze how each of this object reflect or emitted energy. Because you know, the vegetation is just one class, but you have subclasses, many subclasses, different kind of crops, different kinds of trees or bushes, whatever. So in this class, it's many other subclasses. In water also, you have the sea, the water, the lakes, whatever. Every water body can reflect the energy on his own. The shape of that line is the same, but the energy is different. So soil or bare soil, you have soil within which you can dig, or soil like rocks or sand. It's everything. It's soil or bare land, or also built-up objects. Our human eye can have differences between asphalt, concrete, roof, or every other built-up object or type of built-up object, but it's a big question: does the classifier and the computer, some sort of software, does it can make the difference between that objects? So how we look our environment, how we perceive the environment. So, like we said before, it's needed the source of electromagnetic spectrum. After that, needed the objects which we need or want to see. It's objects on the Earth's surface. After that, the energy flow through the vacuum or atmosphere, and after that, not after that, but what is the biological sensor? Biological sensor, it's our eyes. So we need the eyes to see the objects around us. So light reflects off objects and travels to the human eye and pass through the cornea into the pupil and through the lens. On the sensor, you have the lens also. After that, the cornea and lens bend the light to focus on the retina. Photoreceptors on the retina convert the light into electromagnetic impulse, and the electromagnetic impulse pass along the optic nerve to the brain. So this is the much of medicine stuff or terms, but it doesn't matter. It's the main stuff that the brain needs to get the impulse, like a reflection from the building in this example, and with that reflection caught with our eye, they produce some impulse go to the brain, and brain see everything around us. So we don't see with the eyes, but with the brain. So in our brains, the image or objects arise. After that, the reflection from the car. We see the car. If the reflection arise from the road, we can see the road, grass, water, forest. So every object needs to have a different reflection, because the different reflection cause the different impulse in our eyes to see not some blur, I don't know, the objects or something like that all objects are the same or the same color, but every object have the different shape, and here it's the different color and hue and saturation. So that's process the man took, and the human took, and create the sensor. The sensor do just the same, but it doesn't biological one. It's a hybrid one, hybrid system to create the images. Every object hit the sensors in different way with a different strength, and the images or the objects on the image were created. So it's this was for the images which we took every day, and which are produced by reflection. But if we want to, if someone wants to take the thermal image, they need to go in other way. So all objects with temperatures above absolute zero have temperature and emit energy. The amount of energy and the wavelength at which it is emitted depend on the temperature, of course. Higher temperature, the energy is stronger, like you can see this on image. When the energy, when the temperature arises, the amount of energy is also arise, and that move to the left of this histogram, and with you also can confirm this, and what the color is fire, and what the color is the iron when you melt it. So when the temperature go high, all the spectrum move to the visible one, to the visible spectrum, and like because of that we see the stars also in blue or yellow. It's red light, and according to that light and that reflection, or not reflection, sorry, it's emitted energy, the physicist can model it's that's how old that's the stars are, or his galactics. So we already said that, but also once more, the border between reflection and emission portion of spectrum is 3 micrometers. Before 3 micrometers, all wavelengths, all photons are used for the creation of images by reflection of irradiation. After 3 micrometers, that energy used for creation of thermal images. So what electromagnetic do in atmosphere? It's interaction of electromagnetic spectrum with the atmosphere cause scattering. Scattering occurs when the particles of large gas molecules present in the atmosphere interact with cause the electromagnetic radiation to be redirected from its original path. So on his way through the atmosphere to the Earth, these particles, these photons, hit in these gas molecules and don't go in direction, in straight direction, but they refract, they scatter in a manner of light theory. So it's about size of molecules present in the atmosphere. So the amount of scattering that occurs depends on the size of these particles, yes. Also, the effect of scattering is to redirect radiation so that a portion of the incoming solar beam is directed back toward space as well as toward the Earth's surface. So it's every direction. We don't know in what direction they go, but they redirect from the first path. So Rayleigh scattering, it's the scattering known also like scattering of a clean atmosphere. That's the scattering from the natural particles in the atmosphere, and even we don't live on the surface of Earth, the nature product that particle of atmosphere. So just ozone, oxygen, water. So everything what the nature product. So typically such particle could be very small specks of dust or some of the larger molecules of atmospheric gases, such as nitrogen and oxygen. So it is the domain scattering process, dominant scattering process, high in the atmosphere, up to altitudes of 9 to 10 kilometers, the upper limit for atmospheric scattering. So that scattering occur mostly it's 9 kilometers from the Earth and up. So that scattering is wavelength dependent. So you can see that smaller wavelength, or photons in the smaller wavelength, are much scattered than bigger wavelength. You can see it from blue to green, and because of that, Rayleigh scattering is the cause of both the blue color of the sky and the brilliant red and orange color often see at sunset. So why? On his diagram, this picture on the down right corner, it's depend at way to radiation enter to the atmosphere. If they enter perpendicular, then the most scattering particle are blue. But if you go with some angle in atmosphere, then the blue particles have the problem to enter in the atmosphere, and then the larger amount of the other wavelength are going through the atmosphere. So around the noon, you can see the blue sky or blue sea, and that's the main example and proof that the blue, we call blue, that the human call that kind of photons on that waves, we call them blue, and that's the reason why we call the blue sky or blue sea. But when on the sunset, on sunrise, like I said, the blue portion of spectra, it's going to atmosphere in a smaller amount, and they scatter in the upper atmosphere. But in the down, we can see that like red, orange, or yellow, because the more red wavelength enter to the atmosphere, and then they scattering in atmosphere. Mie scattering is the second one, and it's caused by large atmospheric particles, including dust, pollen, smoke, and water droplets. And Mie scattering is wavelength dependent. So, but not in the simple manner of the like Rayleigh scattering. It depends on the to be greatest in the lower atmosphere, where larger particles are abound. So the main scattering Mie of Mie have took a place 5 kilometers from the, it's from the Earth's surface to the 5 kilometers from it. And finally, non-selective scattering, that's a scattering that don't depend on the wavelength. How I know that and how I can explain to you, you see the clouds. When all photons or all wavelengths reflect in the same portion, then you can see then you see the white color or white light. So you can see these clouds are white, not yellow, red, blue, or whatever, that white. So that's the proof that the all wavelength of energy or all wavelength reflect in same amount. So what is important consequence of effects of scattering for remote sensing? So because of the wavelength depends of Rayleigh scattering, radiation in the blue and ultraviolet regions of the spectrum is usually not considered useful for remote sensing. So mostly the experts, when have some analyze some precise analysis of some objects in atmosphere, they cut the blue portion of spectrum. So they use just green, blue, green, red, and infrared, and the blue one cut from the, or don't use the images in blue wavelength because of you see right now. So images that record this portion of the spectrum tend to record the brightness of the atmosphere rather than the brightness of the scene itself. But when someone analyze the scene, they want to have the reflection of the objects more rather than from some blur from the blue portion of spectrum. So for this reason, remote sensing instrument often exclude short-wave radiation. So the other aspect of the electromagnetic spectrum and the interaction with the atmosphere, I already said before. So in contrast to scattering, this phenomena cause molecules in the atmosphere to absorb energy at various wavelengths. So like you see on this image, the energy doesn't go further than this particle which exists in the atmosphere. In right lower corner, you can see what cause additional source of problems, or carbon dioxide, or whatever. So you can here it's read the good ozone. Good ozone, it's on the upper part of the atmosphere, but in down there it's much more this Malik partial, like said, it's a partial, so which caused the big problem. So absorption of radiation occurs when the atmosphere prevents or strongly attenuates transmission of radiation or its energy through the atmosphere. Three gases are responsible for most absorption of solar radiation. So it's ozone, carbon dioxide, and water vapor. So ozone, like we said, it's Rayleigh scattering. It's a scattering of the clear atmosphere. So the ozone are in atmosphere after some hurricanes or something like that. That's kind of weather produce the large amounts of ozone, and they preserve on upper part of the atmosphere. But carbon dioxide and water vapor, it's rather stay near to the surface of Earth. So remote sensing gets tools for also for monitoring the ozone in the atmosphere. So on the left side, you can see the state of ozone in 1979. And on the right down, it's 2011. So you can see the ozone hole. Here, when the monitoring is starting, you can see that the ozone was in the middle of that ratio, but nowadays, or in 2011 and today also, they go to the zero, to the blue or this violet part of this range, and that is not good for mankind. On the right side of this image, you can see the concentration of the ozone in 206. So it's you can know that the ozone are in smallest amounts in the parts of Earth where the industry is high. It's higher than others. So it's also carbon dioxide. It's the same. You can see the where you can find the more amount of that's problem, that's carbon dioxide on the Earth. That's also can be reached. These results also can be reached and is reached by means of remote sensing by the satellite. Not images, but the satellite information. A satellite who measure that kind of information in atmosphere, and the experts can create thermal map like no, not thermal, but thematic map like that. This. So the next effects of absorption. It's atmospheric windows. I said before that's some part of spectrum doesn't going through the atmosphere. So the absorption of that wavelength of that photons, it's large. And this image illustrates that. So this yellow surface, or yellow surface, there's it's energy that do not pass through the atmosphere, like you see this teeth of whatever of tiger teeth or what, how you will call it, and down the second image show it's vice versa. It's a yellow area show us the energy who pass through the atmosphere without problems, or with small problems, small amount of dead particles. This wavelength the atmosphere absorbed. So these atmospheric windows are very important for someone who wants to deal with the remote sensing, because you can show what part of electromagnetic spectrum you can use to gather the information about objects on the Earth's surface. So the place, so it's mainly linked with the electromagnetic spectrum, not to atmosphere, because every part of electromagnetic spectrum have to have problem with the propagation through the atmosphere, or it's almost the same in Europe, in Africa, in Asia. It's wrong to say that's the place where energy passes through the called atmospheric windows, because someone can thought that okay, there is space in atmosphere where that part of spectrum doesn't through the atmosphere, and in other part does. No, it's a link with the range of electromagnetic spectrum. For some ranges, the atmosphere is closed for that. So people said that the atmosphere window for that part of electromagnetic spectrum are closed. For other, the windows of atmosphere, it's open or wide open for that wavelength. So here you can see the major atmospheric windows. It's first one, it's from ultraviolet to visible. It's for 0.3 to 0.9 micrometer. It's the ultraviolet, visible, and near infrared. Here it's a mistake. It's not near infrared, but short infrared. I need to correct that. It's a short infrared from 1.5 to 2.4 or to 3. But from 2.5 to 3, it's atmosphere. It's rather closed. Here is the thermal infrared. It's from 8 to 12.4. It's for thermal images, and the thermal camera, it's mostly work on this wavelength. And microwaves, it's from 7.5 millimeters to the X meters. Once again, this white surface, it's a usable energy, and this blue surface, it's the energy which the atmosphere absorb. And on the end, it's a refraction. It's a problem of going through the atmosphere. It's a refraction. It's is the bending of light rays at the contact area between two media that transmits light, because two media is it's vacuum and atmosphere. So when the electromagnetic spectrum reach to atmosphere, they change the path, and that's we call the reflection. Here it's better to talk interaction with the atmosphere. Like we said, it's just a recapitulation. The source came from the sun or from some source, and the scatter in you can see the scatter in atmosphere. That's electromagnetic waves which don't have a large problem to going through the atmosphere. They came to the surface and reflect, and going up to the sensor. If we talk about emission, also every object emitted energy, and energy go to the sensor and also go through the atmosphere and have the problem with the scattering and with the absorption. And here is a problem about cloud, gases, aerosol, and every other particles which can be found in atmosphere. So we say about this, it's where energy reach to the ground, to the Earth's surface. Some part of energy absorbs, and large parts of energy reflect from the surface to the sensors, or also to the atmosphere again. I will now finish with this in the interaction with the. Yes, I finished. Sorry, it's a bit more time, but I need to finish that because all that technical problems. So interaction electromagnetic spectrum with the vegetation. In leaves, in every kind of vegetation, so chemical compound in leaves called chlorophyll strongly absorb radiation in the red and blue wavelength, but reflects green wavelengths. So because of that, we saw the health vegetation like green. I didn't said before, but every object reflect energy in different manner, and the strongest wavelength that object reflects, that's the color we saw on this object. So if you wear a blue blouse or trousers, whatever, someone around you see you have the blue clothes. But if someone have the red portion of spectrum reflect the most. That's like with the vegetation. So the chlorophyll is, or the vegetation is object, that's natural object which produce that chlorophyll. That's the gas. So we cannot see them, but if you calculate the vegetation indices or look in image which collected in infrared part of spectrum, you can see the content of chlorophyll, but not it's a nominal number, but you someone can see where the chlorophyll are in bigger amount and where in smaller, just like that, like monitoring. So leaves appear greens to us when chlorophyll content it at its maximum. So maximum chlorophyll, the vegetation is greener, and in infrared image vegetation it's lighter. We will see that tomorrow. So in the internal structure of healthy leaves act as excellent diffuse reflector of infrared wavelengths, like I said. But when the leaves go to the end of his life, of whatever they call, the near infrared portion, it's weaker, and we don't see anymore the leaf like a red one, like a green one, but like some dark or brown one. Water have the main reflection, or the larger portion of reflection is in the blue and green one. So like we saw the rivers like blue or green, and the smaller reflection have in infrared. So on infrared image, the water are dark, and on the image in the visible spectrum, when we create the image in the color, we saw the water in blue light. And according to depth of the water, the color is also different. So thus, if there is suspended sediment present in the upper layer of the water body, then this will allow better reflectivity and bigger appearance of the water. So on the other hand, if you see the bottom through the water, the reflection will be bigger, because the reflection isn't just from the water, but from the sea level. But if you don't see in some port or harbor, if you don't see the object in the water, if you just see the water body, that's the reflection is smaller, and on the image you can see like not that blue kind of image, like the shallow water. This image I want to leave for tomorrow. it's better because it's essence of the remote sensing. I can talk or explain on this slide. So for today, it's that's it. And if you some question for me, please ask. If you do not, we will tomorrow. We will see tomorrow at 1 o'clock. So hi for today.
Thank you very much.
Thank you.
Thank
Thank
you.
you. Thank you very much.
Thank you very
Thank
much.
you.
Thank you very much.
Thank you,
Bye.
Mr. Andrea.
No problem.
See you tomorrow.
Yes.
Thank you.
Thank you. See you tomorrow.